We talked about how like charges repel one another and how unlike charges attract. We talked about how when charging by induction, the presence of positive charges pulls nearby electrons, negative charges towards the positive charges. A nearby negatively charged rod will push the electrons in that conductor away, allowing you to charge an object by induction. Well, physics deals with quantification, right? We want to quantify this force. We just don't want to talk about it being a repulsive or attractive force. We want to assign a number to it. So that number is determined by Coulomb's law. So Coulomb's law actually is the mathematical expression that allows us to calculate the force between two charged objects. So Coulomb's law is given here in this boxed area. The force between two charged particles is equal to lowercase k. Now, previously last semester, we used lowercase k for spring constant. That's not what it's being used for here at all. Lowercase k is equal to, it's the electrostatic constant, if you will. It's equal to 8.99 times 10 to the 9th newtons per meter squared over coulombs squared. Q1 times Q2, those are the charges on each of the two objects. There's absolute value signs here because, well, if object 1 is negatively charged and object 2 is positively charged, then that will give you a negative answer. We're not interested in the negative or positive aspect of the answer. We want the magnitude of the force. We'll talk about the direction in a bit. So we use absolute value signs to get the magnitude of the product of the two charges. And we divide that by the distance between the two charged objects squared. So those constants are listed here. Now I think your book might use 8.988 times 10 to the 9th, which takes it to 4 significant figures. So technically 8.988 times 10 to the 9th, that works as well. If you need the extra precision, you should use that value, but 8.99 will work for most of the problems you're dealing with. The units here are all SI units because they cancel, right? We need force in newtons. So when I use K, K has newtons in it, but it also has meters squared over coulombs squared. This distance, SI units, are going to be meters. That's squared. So this denominator will have meters squared, which will cancel those meters squared. The numerator is the product of two charges. The SI unit for charge is the coulomb. So coulombs times coulombs is coulomb squared, which will cancel this coulomb squared in the K term. So this value, this constant term, is just there to make sure the units work out. So you have to make sure that your charges are in coulombs, not microcoulombs or nanocoulombs. You have to make sure your distances are in meters, not centimeters or kilometers. And you will get using that constant, you will get a force out in newtons. So if everything is SI, you have nothing to worry about. So what is actually happening here, I have it drawn out. So if we have a positive charge, Q1, sitting some distance r away from a negative charge, Q2, there is a force between these two charged particles. Well, we can calculate the magnitude of the force from this expression, but how do we know what the direction of the force is? Remember, force is a vector. It has both magnitude and direction. Well, the direction just depends on the types of charge. If they are oppositely charged, like they are in this example, the force is in a line between those two because it's an attractive force. So if these are two particles placed on the horizontal axis, the force will be attractive together in the horizontal axis. If these two objects are placed on the vertical axis, the force will be vertical. If they're placed offset, the force is still on a line connecting those objects in an attractive direction. Now, if these are like charges, if they are both positively charged or they're both negatively charged, then they would repel one another, and the forces would be, in that case, away from one another. Still on a line connecting the two, but now moving away rather than towards. Note the similarities between the form of Coulomb's law and Newton's law of gravity. Newton's law of gravity, which I'll write down here, F sub g was equal to the gravitational constant times m1 times m2 over r squared. This is Newton's law of gravity, universal gravitation. It's a similar format. A force is equal to some constant term. This was the gravitational, universal gravitational constant. This you can think of as the electrostatic constant. The product of the masses rather than the products of the charge. No absolute value sign is needed because mass is always positive. And the distance between them, oops, distance between them squared, not R2, the distance between them squared, which is the same as it is in Coulomb's law. So these forces are known as inverse square forces. As R gets bigger, the force rapidly drops with the square of the distance. So charged particles twice as far away, the force drops by a factor of 1/4. 3 times further away, the force drops by 1/9. 4 times further away, 1/16. 5 times further away, 1/25, and so on. It's an inverse square relationship. Now, calculating Coulomb's law, so the force on particle 1 from particle 2 is up and to the right in this example, because these are opposite charges. Force on object 2 from object 1 is down and to the left towards object 1. If you added a third charged particle, you would need to calculate the force on object 1 from each of the charges. So say I have 5 particles. What is the net force on object 1, on charged object 1? Well, that depends on the force on object 1 from object 2, plus the force on object 1 from object 3, plus the force on object 1 from object 4, plus the force on object 1 from object 5. You would add those vectorially. Just like if you have multiple objects all pulling gravitationally on one another, you have to calculate the individual forces and then add them up vectorially to get the net force of gravity on the object.